Aloha class, let's finish this improper integral thing. The first half of this lesson, the first part, right? We had improper integrals where we had limits where infinity was involved. Okay? But now we're dealing with these different types of graphs. Now to give us an introduction about what's going on right here, we're going to plug these guys into our calculator. I already did it for you. I get 1.430. For this guy here, I get 1.485. If you notice something, there's something interesting happening here. It's kind of like if the bottom limit was 0, which actually would be kind of improper, right? Because you can't have a 0 there, because if you did, that's 1 over x to the 1/3, and 0 is not in the domain. Now, believe it or not, this looks like it converges to a specific value. And if you were to graph 1 over x to the 1/3 in your calculator, what you're going to find out is there is an asymptote at x equals 0, but it gets there super duper fast. And that's why it's able to converge, right? Remember, we looked at 1 over x and 1 over e to the x when we were dealing with x going to infinity. But now we're dealing with some asymptotes. And believe it or not, we could still get limits or integrals or areas that converge, and we will get some that also diverge. Now, here's an example of 1 over x to the 3rd. And if you were able to look at this graph, there is a vertical asymptote there again, but it doesn't get there as quickly. So guess what that answer is, class? Holmes says it diverges then. Well, let's go ahead and take a look at it. We plug these guys in our calculator. Oh my gosh, that's a big number. If I get closer to 0, guess what? I bet you I get even a bigger number. And then if I plug that guy in, which is pretty darn close to 0, it goes a little crazy, right? So that would mean it diverges. And that's the whole point of the second part of improper integrals. Okay, when we recognize an infinite discontinuity at an endpoint, okay, and actually it doesn't even have to necessarily be an endpoint, okay, and we'll find that out in a little bit. We have to set up a one-sided limit. When the infinite discontinuity is on the interior, we have to set up two integrals, just what I was kind of talking about. We approach the vertical asymptote from each side. So what the heck does that mean? Because we're going to have to do this algebraically, aren't we, Holmes? Bears, come on. Bears, Cowboys tonight. Let's hopefully we all wake up happy tomorrow. Come on, I'm wearing the lucky, ugly sweater shirt. All right, here we go. So when I look at this problem, I should ding, 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 red flag. In the past, right, we would say D and E for this guy because of that guy right there. But actually, maybe I might be able to get an answer for this. And the way that I'm going to examine it is not by looking at it graphically, but we're going to do this with improper integrals. So the guy messing that up is the 0. So we're going to do the limit as b approaches 0. Now, whenever we're doing this, we said earlier that this has to be a one-sided limit. Okay, and if I'm between 0 and 1, hopefully it makes sense. If I'm going from 0 to 1, I'm going to go from 0 on the right side, okay, and then I'm going to go all the way to 1, right? Wouldn't that make sense? It was from the left side, it'd be like -1 to 0. Kind of makes sense? If not, come see me in the morning, okay? So then that's b to 1 of x to the -1/3 dx. Okay, then we're going to do a little math, right? Do a little antiderivatives. Okay, antiderivative of that guy, we're going to add 1. That gives me a 2/3. Divide by 2/3 or multiply by that reciprocal. And then we're going to evaluate from b to 1 using the fundamental theorem of calculus. So we get the limit as b approaches 0 from the right. Let's go ahead and use that. I get whoops, 3/2, right? Because that's to put a 1 in there. And then we get minus 3/2 b to the 2/3, right, class? And then what it is we're going to have to examine this little piece of it right there. Now, believe it or not, if I can plug in a 0 and get an answer, I'm just good to go. Okay, so let's plug in a 0, and I get 3/2 minus 0. So what's my answer? 3/2. Not bad, right, class? Not always that okay, though. Okay, if I go ahead and plug that guy in and it still gives me the red flag, well, then I have to examine it a little bit more. Maybe that happens with this next example. Let's take a look at it. Okay, red flag again. In the past, we probably might say D and E for this, but you found last time it might not be D and E. Now we got some more tools in the toolbox, right? So here we go. 0 once again messes that up, so we're going to go ahead and do a one-sided limit. Once again, we're going from 0 to 1. So that means I'm going to be coming from the right side of that asymptote, right? So that's why I have that one-sided limit there, and then we're going to go from b to 1 of x to the -3 dx. Okay, so then we got the limit as b approaches 0 from the right-hand side. A little antiderivatives, add 1, divide by it, right? There we go. We're going to evaluate it from b to 1 using the fundamental theorem of calculus. Okay, so we plug in that 1. Oh, I get a negative 1/2. Sweet, 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 sweet. Okay. Now I'm going to put in the b. It's going to end up being a plus. Okay. And then, yeah, like always, write at least once a class period. All right, so let's check it out. So if I plug in that b, sorry I got distracted, it's going to be a plus a 1/2, and then it's going to be a b to the negative 2. Okay, and I can't plug a 0 in there, right? Ooh, don't forget that right thing. Okay, I can't plug a 0 in there because if I plug a 0 in there, I get 0 to the negative 2, which is a d and e. So I just got to think about this bad boy for a little bit, okay? There's going to be an asymptote there. If I put a 0 in there, the asymptote either goes to infinity or negative infinity, correct? And that's the graph of 1/2 1 over b squared. Okay, and that guy is going to grow equally fast just like that. So we kind of want to know what the graph looks like to be able to evaluate that. And if I approach 0 from the right-hand side, I'm going to positive infinity. So I'm going to end up getting a negative 1/2 plus an infinity, which is an infinity. So we say that this bad boy diverges. How about it? Not bad, right, class? Kind of similar to what we were doing. But this time, it's because we have some infinite discontinuities or vertical asymptotes, okay? All right, example 14. Okay, let's try blue maybe this time. All right. Whoa, that guy's in the bottom. Says we're going to go to 27, but 27 wouldn't be good, right? That wouldn't be in my domain. That'd give me a D and E. But maybe I could still get it. Maybe I'll get an answer. So I'm going to set up a one-sided limit. So we're going to go the limit as b approaches 27. This time 0 to 27. 0 to 27. So this time, I'm going to hit the 0, 27. I'm going to hit the left side. So it'll be 27 from the left this time. Does that make sense? Doesn't. Come see me. From 0 to b. Okay, let's rewrite this. That'd be 27 minus x to the negative 1/3 dx, right? Okay, so we got the limit as b approaches 27 from the left. Okay, now let's do a little anti-derivatives. Okay, and we're going to get 27 minus x. It's kind of like a u sub, right, class? Add that. I've got to divide by 2/3, or that'd be a 3/2. And then I also have to take care of that negative, right? Because on u sub, I'd have a negative right there, and then we're going to evaluate that from 0 to b. Once again, if you got to do u sub, go ahead. But I hope you're trying to do it without using u sub because it's kind of a really nice time saver, right, class? Okay, so let's go ahead and look at this. We're going to use a little fundamental theorem of calculus now, and I get a little negative 3/2. What do we get? 27 minus b to the 2/3, okay, plus 3/2, okay, because 2 negatives makes a positive, okay, 27 to the 2/3. Okay, now we're going to do a little math. Now the question is, can I plug in that 27? That's a positive exponent. For sure I can. So that's just going to give me a 0 because 27 minus 27, 0. I can do 0 to the 2/3, right? If that was a negative exponent, that would be light bulb, red flag. I better know what the graph looks like. But I can just use direct sub there. And then I just have to do a little math right there. Remember, I heard people in the class saying it the other day, you better take that cube root first. Cube root of 27 is tree. Tree squared is 9. And then if you do all that math, what do we got? A little 27 over 2. So how about it? That guy converges. Okay, what does that mean graphically? It means it gets boom, boom, goes really fast to that asymptote, which would be at x equals 27, right? Grows really closely, so we're able to find that area. Oh, snappity-dappity, 0. 0 usually means bad, but 0 is okay there, right? I can plug a 0 in there and get an answer, right, class? So snap, but 1 is not good, and guess what? 1's in there. Before we got to BC, we would just say D and E for that bad boy. No, right? So let's go ahead and look how we get an answer for that. Okay, so here we go. How are we going to break this bad boy up? Well, I know I need a limit, and I need it to be a one-sided limit. Okay, so we're going to go to 0 to 1. Okay, so if I'm going to go to 0 over to 1, 0 to 1, so that would be to the left side. Okay, so we're going to go 0 to 1 from the left side. Okay, and then I'm going to rewrite that as x minus 1 to the negative 2/3. Okay, so that's one piece, but then I got to add it together, right? Because I got to go now from 1 to 3. But this time, and I'll use C, we're from the right side of 1, right? Because we're going to go from C to tree, right? Okay, coming for help again if that little left-right side is not making sense. Sometimes some of us struggle with that little piece of it. Little anti-derivatives, right? So we're B as B approaches 1 from the left. Anti-derivatives, let's see. This is just a U sub, and guess what? That derivative's just 1. So now I just have to add 1 and divide by that guy. Oh, easy peasy, Japonesey. And I get that guy, and then we're plus. Still a limit here, so I've got to keep it as an improper integral. Anti-diverse. Oh, same problem. That's kind of nice. So I just have to rewrite that. There we go. Little fundamental. Oh, sweet. I get to do it 2 times. Okay, I get to do it 2 times here. We got b approaches 1 from the left. Let's go ahead and do some subs. 3, that's a b minus a 1 to the 1/3 minus, put a 0 in there. A 0 in there would be a -1. Ooh, that's going to end up being a positive tree, right? And then we got plus the limit as c approaches 1 from the right-hand side. This time I'm going to plug the 3 in first, and I get 3. Ooh, I get the 2 to the 1/3. I don't know what that is. What a what? And then I got a minus a 3, and then I got a c minus 1 to the 1/3. Okay, now if I notice I have no negative exponents, sweet, sweet. So that means I can just plug in the 1. You plug in a 1 in there, and you get 0, okay, plus 3. And then I got this guy, and then I get 3. That'd be like the cube root of 2. And then I can plug a 1 into that bad boy there, and I get 0. And so if I simplify, that's 3 plus 3 cube root of 2. That means it converges. How about that? Means it goes to, they both go to that asymptote, which is at x equals 1. So whatever this graph looks like, you got like x equals 1, and it just goes, right? Goes really close, okay? So I'm able to find the area of that bad boy, all right? All right, we're rolling. We just got to do one more, and then believe it or not, I'm giving you some homework, and some of you have been getting a little lazy on me with the holidays coming up, so do not get lazy, please. All right, here we go. Find the area. Okay, we did that in AB. We're in the 4th quadrant, okay, of this graph, and we all should be able to graph that, right? If it's a natural log, then we all know the one point we always want to use is 1, 0, right? And that's my natural log graph. So what they're asking me to do is find the area between that curve, the x, and the y-axis. So they're asking me to find that area there. And I don't know about you, but it looks like it gets there kind of quickly, right? So guess what? This brings up the idea that goes infinitely, right? So once again, it's an asymptote, though. So how am I going to use the knowledge from this section to solve this problem? Okay, how do we do area problems? Well, we do the area. Okay, correct? We're the area. And in this situation right here, what am I going to do? I'm going to go from 0 to 1, right? Because I'm a little dx, right? Everything's in terms of x's. Let's keep it that way. Okay, 0 to 1. I've got my rectangles, right? My rectangles don't really get broken up, okay? So I'm going to go a little top minus the bottom, right? So what are we? A 0 minus, right, class? Okay, 0 minus, right? Because that's my rectangle, top minus bottom, 2 natural log of x. Okay, and then I'm just going to do work, right? That gives me the area, but I'm going to have to do it with an improper integral because we're going to do it as as b approaches 0, and we're going to do that from the right-hand side, and we're going to go from b to 1 of -2 natural log of x dx. Now, I don't know about you, but I'm not liking that -2 right there, so let's go ahead and bring out that -2, okay? So we got that. We're going to bring out that -2, and we're going to evaluate the integral from b to 1 of the natural log of x dx. Now, I'm not going to waste our time, but we've done that problem in our Zorro, okay, in our Zorro. But I'm telling you right now that that is a integral, an antiderivative that you want to have memorized. Ooh, I forgot a little negative sign I just noticed right there. So I'm going to write it out here, but I'm telling you right now to memorize this bad boy, okay? That is x natural log of x minus x. And if you don't believe me, go ahead and do your Zorro or tabular method and see that that actually does work out, okay? And we do that from b to 1. All right, so now we're going to do a little fundamental theorem of calculators, okay? And I'm going to plug in that 1. Now, if I plug in a 1, I'm going to get 1 natural log of 1, which is 0 minus 1. Everyone with me, right? If I plug that 1 in, okay, hopefully that's okay. On this other one, we're going to subtract, plugging a b in, which would be b natural log of b minus b. What the heck's going on? Okay, so let's go ahead and take a look at this. It's going to be -2. Ooh, snap. Let's bring that limit down here, right? And then I'm going to get -1 minus b natural log of b plus b. Okay, now can I plug in a 0? I can plug a 0 in there, right, class, and I will get 0. Okay, now what about what's going to happen when I plug it in for that bad boy right there? All right, now thinking about that bad boy, there's a lot involved here. Believe it or not, it has a lot to do with L'Hopital's rule. Now I'm going to show you it in a moment, but this ends up being 0. You end up getting 0 times infinity. That's indeterminate, okay? But that ends up being 0, and that ends up being 0, so I get a final answer of -2 times -1, which is 2. Now, to go with that right there, now, darn it, AP exam, you would probably have to show this, right? This is where they want you to show L'Hopital's rule, okay, where you get b times the natural log of b. Okay, well, I can kind of rewrite that, you guys, and that doesn't look like L'Hopital's rule. But anytime you get an indeterminate result, and I'm almost certain that this is no longer a BC topic, okay, but I could rewrite this like this, which gives me a 0 over 0. Whenever I get a 0 over 0, remember, you got to share that limit to both of those guys. We did it in class. Okay, that means I can take the derivative of both of those guys, which would give me 1 over b, and this would give me -b to the -2. Now, if you do all of that work and do a little simplification, you get a -b. Now you can plug in the 0 and you get 0. And my pen ran out, but who cares because I'm done? Okay, but that's how it works out. But I guess real ghetto is that would be 0 times infinity, which is indeterminate, and it is 0, and I should show that. But using L'Hopital's rule, which I did there in the blue. Now pay attention. I tried to keep this video under 20 because we've been watching some long ones. So your only homework here is I need you to do 16, 17, and 18. And just try your best, but you honestly have to try your best. I will check your notes tomorrow in class. Aloha!